Most recently, generative AI and large language models have become an essential part of our life. Today, I would like to address the issue of how can we communicate with large language model. One and the most popular way of communicating with large language models is via prompt and web interface. We can provide a question, what is the capital of the United States? And we'll give the answer Washington, D.C. However, this type of interaction with ChatGPT and other large language models restricts the interaction only to the context which has been already delivered to large language model during the pre-training. And the question is, how can we actually use power of large language models in order to answer the questions which are more context related to our interest? One of the common ways to do that is called RAG, Retrieval Augmented Generation. However, in this video, we're not going to discuss that part. We are going to concentrate on other different ways how we can work with large language models and ask questions to them. So in this video, I would like to address the issue of how can we use the power of large language models to answer the questions about the research papers. I have selected two research papers. One is Attention is All You Need, the fundamental paper about the transformer networks. And the second paper is SBERT. That's another seminal work about bidirectional transformer language models. So our input data are two PDF files. And first thing we have to do is to read these PDF files. There are many ways how we can read PDF files, but in this case, we will have a particular requirement. It's not only necessary to read the PDF file, but ideally we would like to split that PDF file in the chunks, the text inside that PDF file, and then we would like to do some operations with the text. So just reading and recognizing the text and trying it to randomly split into paragraphs or sentences will not really work in this case. So in order to simplify the whole process, I will use LlamaIndex ecosystem. Very briefly, LlamaIndex is a framework or ecosystem which allows to work with your data and allows your data to meet large language models. So in a sense, it's a framework to enable large language model applications. However, in this video, we will concentrate mainly on few functionalities of the LlamaIndex. So the first functionality of the LlamaIndex is ability to read documents in various formats. And in this particular case, we have two PDF papers. Second functional ability of LlamaIndex is to have a vector database. Vector database means that the text which we are getting from the PDF files will be encoded into embeddings using the embedding large language model. And then once we decide to ask the question, we can query against whatever is stored in the vector database. So I will talk in details about this particular approach later in this video. For now, we just need a simple directory reader to read the PDF file. Next, we will input some auxiliary libraries like OS, time, and pandas. And before we use LlamaIndex, we will provide some settings. So first of all, as embedding model, we will use this model, and we will provide it as HuggingFace embedding. Then we will not explicitly provide large language models, and we set chunk size to be 128 tokens, and we will allow 25 tokens overlap for the adjacent chunks. Now, once we apply this simple directory reader, we will provide the directory where our PDF papers are stored. In this case, this is directory papers in the same directory where this Jupyter Notebook file is located. And we will provide a key recursive. In this way, we will be able to extract the chunks of text for each PDF file separately. So once we run this simple directory reader, we will get a reader object as an output, and the reader object will have the following properties. So there is very convenient basic property in Python object __ dict __. It will basically showing you how the object is organized from a point of view of the dictionary. And then you can get a lot of information about the object just with this command. So for example, we can see that we are in recursive mode, and we can find the directory, which is papers, and then the input files with actually Windows path. We will have two files: attention is all you need and BERT. And other, you can have more auxiliary technical information. So now if we go ahead and call this __ dict __ input files, we should get actually only the input files. We can also do it in a different way, just calling reader dot input files. So this will work either way. The main point of using the __ dict __ is to get the list of the properties available for this object. So next, let us store text chunks into dictionary and trace chunk paper mapping. For this, we will create a list of PDF files. We will read it from here. We'll create a list of documents, or in other words, it will be the chunks of the text stored here. The reason why I call it all docs is because what LlamaIndex will do, it will take the PDF, reads the text out of it, chunks the text into pieces, and then output for each chunk of the text an object which is called document. And how that object is organized, again, we will see later, very soon. So in this all docs list, we will store all the docs one after another. However, we will also create a docdict in which we will use the paper name or PDF name as a key. So you will see how it's all done. We will iterate through the reader object with the iter _ data. And for each iteration, we will get a list of documents which were extracted for a given PDF file. And then we will also use an index to enumerate that. So for each PDF file, we will have a name, PDF name. So we will extract it from the complete path of the input file. And then we will print out which file we are processing right now. So for the docdict, we will use a PDF file as a key, and we will add all the documents or the chunk of text wrapped into the documents under this key. And if this key does not exist, we just create a new key and provide a set of documents for that. On the other hand, for the list of documents, which is all docs, we'll extend it with a set of documents. So here you can see we have extracted documents from two files, as expected. And now let's inspect the structure of dot _ dict. So we have two keys as expected, the name of the first paper and the name of the second paper. And here is the whole object as is. Next, we can check how many chunks were extracted from each paper. So we can run the following command. We can pick the key, which is the name of the paper, and this should output us a list of all the chunks. So then we can take the length of that list. And in this case, we find that for attention is all you need, we have connected 15 chunks. And for BERT, we have connected 16 chunks. Now for attention is all you need paper, we will take a first document and investigate how that document is organized. So again, we will apply __ dict ___ property of the document in order to see what's inside. So first we see the document ID, some meta information, which contains file name, file path, application, and file size, and so on. And then we also see the text property, which contains the text chunk which has been extracted. So again, we can refer to these properties using ___ dict structure, or we can call directly these properties with a dot. You can see the result will be the same. And finally, in total, we have collected 31 chunks. As we know, for attention is all you need, there are 15 chunks, and for BERT, there are 16 chunks. And this is confirmed by taking the length of all documents which we collected in parallel. So before we continue to interact with LLMs and implement question answering, I would like to do a couple more preparation things. So first of all, we can get a distribution of chunks across the papers, also we can use doc_dict and loop through the keys, and then we can get the length of the lists belonging for each key, and then it should give us explicitly number of chunks for each of the paper. And also we will need one more transformation. So until now, all our chunks of texts are distributed across the LlamaIndex documents. We need to call the document, get the text property, and then we will be able to get the text out of there. But for one of our applications, we will need the whole text of the paper in one variable. And we will create this by introducing papers dictionary. So this papers dictionary will take keys and as articles or research papers. So we will look for the articles, which are in this case 2 papers, the attention and BERT, and then we will collect all the chunks of text corresponding to that particular research paper into one variable. In this case, this will be a dictionary record with the key which has the paper name. And finally, we will do one more simple preprocessing. There are multiple /n sequences inside the text. So we want to get rid of these /n sequences, and also we would like to separate sentences with a period only without using /n. So once we do this, then we will clean our text. So let's have a look of how the text, for example, for attention is all you need looks like. So attention is all you need will be our first article. So this is our text, which we have extracted. So let me remind you that first we have extracted the separate chunks using LlamaIndex data loader. Then we have joined all the text chunks into one long paper body. So finally, let's start implementing our QA tasks and ask questions about the paper. So first, we will start using Roberta-based Squad 2 distilled model. And this is the model from HuggingFace Model Hub. So we will use Transformer library by HuggingFace, and we will input auto-model for question answering, auto-tokenizer, and pipeline. And also for some auxiliary purposes, we will use Torch directly. So at first, we will create a DFS dictionary, which will contain all our data frames. You will understand how each data frame will look like. So we will store the data frames for each question under the key of this given dictionary. So after we are done with all the questions, we will have the data frames corresponding to a particular question. Here we provide our model name, and the model comes from a deep set. And then we set the device. So this is why we need Torch to set the device. In my case, I have a CUDA GPU on board, use CUDA. Otherwise, we will have to rely on CPU. And here we define pipeline. So pipeline is a high-level wrapper, which is basically taking together the model itself, the tokenizer, and it has other useful properties like device. So by using a pipeline, we will actually set up the entire flow from loading the text into the model and tokenizing it and doing further processing for question and answering. And finally, let's ask our first question to a large language models. So for this purpose, we will run through the papers because we will be asking a question about each paper separately. So we will use the same question, which is what is attention? However, this question will be asked to each paper. And for this, we will create another dictionary, which is called QA input. So we will have a question key, which will contain our question, and we will have a context. This will be the variable containing the full text of our paper. And then we run the pipeline with this request, and we will get the answer from the res variable and the scores from the result variable. So what the score does, the model evaluates how well the answer corresponds to the question. In this case, we will have two answers. One answer for the attention is all we need paper, and the second answer is for SBERT paper, and we will also have the corresponding scores. So once we run this, we will also create the entry into our IDFS dictionary with the key, question, and model. And this dictionary will contain a data frame, as I have mentioned earlier. So the data frame will have the following columns. Question, which will be multiplied by a number of papers, and it will contain question. Model name will be multiplied by a number of papers, so we'll have a list of 2 in both cases. Then we'll have a paper name, and we will have answer list and the score list. So that's how our data frame will be organized. So after we run this, we will have our data frame having the same question, because we are asking the same question to different papers. We have the same model, because we're asking this question using the same model. Then we have 2 different papers and 2 different answers. So the first answer is mapping a query and set of key values, and so on. And the answer from the SBERT paper is very simple, all you need. And then the score is 0.35 for the first paper and 0.80 for the second paper. One problem here is that we don't see this text fully in the column. So one way we can fix this is by using the data frame property. So let's try to set the pandas set option display max column width 500. Once we apply this property of the pandas data frame, now you can see that we have the entire text of the answer visible. So now let's go ahead and ask a second question. So what types of attention are defined? In this case, we use the same setup, but just provide a different question. And the data frame will be also a new data frame for the key with the question, which is a new question, and the same model name. And here you can see that the answer to what types of attentions are defined. The answer from attentions all we need is structured attention networks with score 0.67. And from SBERT, we have bidirectional self-attention with a very low score. Personally, I think that bidirectional self-attention is much more closer to the ideal answer than the structured attention networks. But you see the controversial thing here that the score for the answer more likely to be correct is kind of very small. So that's one of the controversial we can see here. So let's note it, and we will consider later how to deal with this. For the sake of exercise, let's just do one more question. So what is a multi-head attention? So we pretty much use the same code snippet. And once we run this, we will have now the answer that what is a multi-head attention. We'll have an answer of self-attention with a value 0.62. This answer comes from attention is all you need paper, and then multi-layered context with a very, very low score. And I think in this case, this is kind of reasonable. The answer comes from the SBERT paper. So what we can learn here is that the answers provided by the model using the QA mode or question answering mode are kind of controversial and actually very short. Let's do one more run, but we just use the pipeline as is. So in this case, we don't provide any model name, so we rely on the default model defined by the HuggingFace. And we will repeat the same questions. So here you can see that the model name is now default. The question is, what is attention? And the answer is multi-head, which is kind of a property of the attention rather than explaining what attention is really is. That comes from the attention is all you need paper, and then from the SBERT paper, few parameters needed to be learned from scratch, which is, again, I don't think this is a highly relevant answer for what we are looking for. And let's do what types of attentions are defined question as well, just to have an idea what is provided. So here we have for attention is all you need paper, the answer is active memory, which has a high score, but again, that's kind of controversial answer. And what types of attention are defined in case of SBERT paper are deeper self-attention, which has a lower score, but it's more relevant than the higher score given for the attention is all you need paper, in my opinion. So finally, let's do the what is multi-head attention question for both papers. And the answers are scaled dot product attention from attention is all you need paper and natural language understanding from SBERT paper. I think both questions are kind of inaccurate, although the first one has quite a high score. So at this moment, we have our dictionary of data frames with keys, questions, and model name. Let's join all those data frames in one data frame. We will call this data frame merge data frame and have a look at that data frame. So here we are. Now we have everything in one place. So we have 3 questions and 6 answers for the Roberto-based squad 2 distilled model, and the same 3 questions and 6 answers to them using the default model set up for us by HuggingFace. So here we will see the paper where the answer originates from, the answer itself, and the score. And let's do a little bit more decoration here. So let's go ahead and do a grouping, so to make the whole data frame look better and kind of easy to grasp what we have. So here we have now the answers grouped by the question. And within the question, we split the answers by the model it were produced. And finally, we provide also the paper where this answer originates from. And here we have finally the corresponding scores. So this concludes the first part of QA. As you can see here, the answers are very short and pretty much often they are not really to the point. So they give you some glimpse of what might be there, but if you know the context of the paper directly, you have a lot of doubts that these are kind of helpful answers. So how to fix this? At this moment, we have used the question answering pipelines and question answering mode to interact with LLM directly. So what we can do different and how we can do different. So instead of relying fully on their LLM in searching for the answer and compiling the answer for us, let's make our hands dirty by text analysis, and let's do the embeddings for the text. So this is the key difference. Now we are going to analyze each chunk of a text separately, and we will try to compare those chunks with the question we are asking. How are we going to do it? The answer is semantic vector search. And here I will explain two ways to do the semantic vector search. The first one will be very, very basic, hands-on, so we will understand the basic steps and how the semantic search is done on a very, very simple level. And then we will apply LlamaIndex functionality to implement the same application, and we will see how it works. First of all, we will need embeddings. So embeddings are the numerical vectors, which are resulting the transformation of text. We use a special type of large language models, which called embeddings large language models. A wide collection of embedding large language model is developed by SBERT and is presented in their sentence transformer library. So from sentence transformer library, we will import sentence transformer. Then we will pick up the model for the embeddings. And in this case, the model is all MPNet base v2. So how we converged and why this model actually is good enough, we can go to SBERT website and check their pre-trained models. So their pre-trained models are coming in different flavors. And here in pre-trained model section, we can find a pre-trained model leaderboard. So you can see that for performance of sentence embeddings, the top network is all MPNet base v2. And similarly to performance semantic search, which we're about to do next, it also provides a pretty good result. It's not the top one. The multi-QA MPNet base.v1 is better, performing the semantic search a little bit, but for the trade-off between these two metrics, I think all MPNet base v2 is good enough. So we will take this model as our basic model for embeddings. So again, embeddings is what we get once we put a raw text into embedding large language model. And this will be our output. This is kind of functional definitions. In more general, embedding is the way to transform text into multi-dimensional vectors, and there are many, many ways of doing this. In this particular case, we are using embedding LLMs to complete this task. So next, we will create a list of queries. In this case, the list of queries will be our questions. So for this particular exercise, we will limit our questions to what is attention and what is multi-head attention. And we will also define a list of documents. So the documents, we will again do some pre-processing. We will append the chunks of text which we collected originally from our PDF files and do a light pre-processing of dropping this /n \n sequence from the text. We have done it for the full paper text. Now we will do the same for each of the chunks. And then we will have still the list of separate chunks. So this document will be a list of slightly preprocessed text. And we don't need to refer to text property of the document anymore because we are reading here the text property directly. Next, we will basically compute the embeddings. So we will have two types of embeddings. The first embedding will be query embeddings, which will correspond to our queries of questions. So we can do it by running model and code and providing our list of queries or list of questions. And the same we'll do for our documents, and we will get document embeddings as the output. So how does the embedding look like? We know that our text is what is attention and what is multi-head attention. And Obviously, these two questions are of different lengths because they contain different number of words or tokens. But what about embeddings? So first of all, embeddings will be of the same length. So no matter how long the sentence is, the embeddings for each of the sentences will be of the same length. So let's check it out. And we will see that we have a response as array. Actually, this is NumPy array. And the dimensions of this array are 2 by 768. So 2 is coming from the number of queries we are having. We have 2 questions, so that's where this 2 is coming from. And what is 768? So 768 is exactly a dimension of our embedding vector. And the reason why it is 768, because this model, all MPNet base v2, is based on the basic implementation of BERT model. And the native embedding size for the basic burst model or base BERT is 768. There is a larger implementation of the BERT model, which has another native dimension of 1024, but here we use the basic one. So that's why the size of the embeddings is 768. And now let's do the same for document embeddings. Let's confirm the sizes. So we have in total 31 chunks, which we confirmed earlier. So these are number of chunks collected from both of the papers. And for each of the chunks, the dimension is the same. So now you can see that the length of the question and the length of the chunks are actually very different. However, embeddings for either of them have the same dimensionality, 768. This means now we can do various operations with these embeddings. So originally we have text which was different in length and was different in origin. Now we have embeddings for each of the text chunks and questions which are of the same dimensions. So let's go ahead and compute the similarity between the questions and the documents. And this is the main difference of approach we apply here, rather than just directly using question answering mode of the LLM. So similarity is computing how similar or how close are two embedding vectors to each other. And there are many ways of doing that. We can use various metrics for this. By default, similarity is computing the cosine similarity measure, which is basically the angle between two vectors. And cosine varies from -1 to 1. So one value will correspond to cosine 1, which is 0-degree angle. So both vectors are completely collinear and we look in the same direction. While -1 will tell us that both vectors are looking into absolutely opposite positions. So as if we take one vector and rotated it 180 degrees. So that will be the answer for minus cosine. And then everything in between will show us the difference in the angle. Another metric which you can use here is dot product metric. We can use Euclidean distance as another metric of similarity, and also we can use a Manhattan distance. To understand how similarity is computed in case of sentence transformer library, you can refer directly to description. So here is a semantic textual similarity article in their website, and they explain how the similarity works in a high level. Then we talk about similarity in particular. There is a special property of similarity FN name, which is the name of the metric of similarity you want to use. And here you can see the whole list. So as I mentioned, by default, cosine similarity is employed, but you can define a different measure of similarity. Let's have a look at our similarity scores. A similarity score variable is a PyTorch tensor variable. So let's convert its values into NumPy. And also we can compute the shape of this. So this is 2 by 31. So we have two questions and 31 text chunks or text snippets. And that's exactly where the dimension of this array comes from. And here are the values. So you can see that values vary drastically. What we can do is rank chunks of text in a similarity order. We can do it by introducing a threshold and looping through our similarity scores and queries, which we have. Also, I will add the query itself, or the question we ask, the document, which will be our chunk of the document, the LlamaIndex document content, and the score. And here what we have. We have a query, or the first question, what is attention? And we can see the similarity scores for a number of text chunks where similarity is higher than 0.25. So you can see the lowest similarity is 0.2585. In the same way, we rank the answers to the question of what is multi-head attention. In this way, we have looked of how we can answer the questions using embeddings and semantic vector search. For this first exercise, we have used the complete chunks of text which we have selected originally. However, now let's do a little bit more inquisitive exercise and let's investigate how different pieces of a given chunk of the text similar to the answer we inquire. Because remember, the embedding dimension is the same for very long piece of text, which is our text chunk, and very short piece of text, which is our question. So obviously, within the bigger chunk of text, will be pieces of the text which are more similar to the question rather than the other one. So let's investigate that in more details. For this purpose, we will select a particular document from the list of our document scores. And we will pick up document 2, which will be our output values. So this will be our document. And then we select query. So in this case, the query again will be our first query. So what is attention? And this is our query, and this is our document. Now, what I want to do is I want to take this chunk of a text and split it into the sentences. To do so, I will use the split operation with the dot empty space delimiter. And this is the result of splitting the chunk into the sentences. So you can see here we have a list of sentences as a response. Now we will do the same operation as we did for questions and text chunks, but now instead of text chunks per se, we will use the sentences within a single chunk. So we will create embeddings for our question, which will be basically the same. And we will create embeddings for the sentences within the given chunk. So now we have only one question. So the response tensor will be one-dimensional. And I want to go ahead and show how the different pieces of the text are similar to the question which we ask within the given single text chunk. Here you can see various similarities for the sentences, and you can see already that the similarity is distributed drastically across this text chunk. So let's go ahead and visualize it explicitly. For this purpose, we will need an auxiliary helper function, which I call a color map. What it's doing is basically taking a value, which will be our similarity value, and using the color map, it will convert it into a numeric value, so which we can use later for coloring the text. One more auxiliary thing we will do, we will use HTML template. So in HTML, which is a hypertext markup language, it's a language used in web to create websites and mark the text, we will use the span tag. So span tag is basically saying, okay, from here to here, this is a piece of text I want to do something with. And we will provide a background color in a style property, and we will allocate the space for the text itself. So text will be our sentence, and the color will be the color corresponding to the similarity measure. So if we run this, we will get this example. So here I provide the color map as some mock similarity value of 0.51, and I provide text. So that's what we'll get the output. So now we need a way. So now we need a way to transform this HTML string into visual, like the browser does. One way to do it is to use display and markdown objects of IPython library. So here we apply markdown to our HTML template string, and then we display this. So this way we are creating the markdown object and then we visualize it. So now we are ready to use our HTML template and to fill it with the particular text and similarity scores. I also add here a little bit of styling. So first of all, I reduce the opacity or transparency, increase transparency of the background value itself. And also in the uppercase, I am providing similarity score between the highlighted text and the question. So now let's run this. And here is our result. So here we have separate sentences. So for example, our first sentence is 3.2.3 application of attention in our model. The transformer uses multi-head attention in 3 different ways, and so on. So this will be our first sentence. And we highlight this sentence with the background color, which corresponds to the value of the similarity score. And finally, after the sentence ends, we provide a similarity score. So how similar these sentences embedding vector is to the embedding vector of the question, which is what is attention, in terms of cosine similarity. That's what the similarity score means in this case. And we do this mocking for all the sentences within the text. And you can see that there are pretty high similarities in the beginning, and then it gradually decreases, and at the bottom the text is almost not readable against the background, and this is done by the purpose because the similarity score is very low. So this is how to do semantic vector search by hands. Now let's do the same using the vector database. And vector database is one of the functionalities which is provided by LlamaIndex. So now we are going back and we will use their objects imported from the LlamaIndex library. So first of all, we will create one more data frame. Now we will call it output data frame. And now we will create an index. So LlamaIndex is called because it's basically implementing the database functionality, and one of the main base functionality is to create the index. So we provide our all docs list, which contains our all documents, and in this case, these documents are LlamaIndex documents, because LlamaIndex needs those documents to create the index and the nodes inside the database, not the raw text. And we use vector store index to do this. Next, we will set a threshold that we want to pick up top k, which equals to 7, similar responses. So next we will create a retriever. So this is the mechanism to retrieve the valid or most similar entry of the database or vector database, which we have just created by running vectors to index. And vector index retriever is another object introduced by the Llama. So we need indexes input, and for similarity top k, we provide a top k variable. So here we'll provide top 7 outputs, which are more similar to the question we ask or to the query we basically run through the database. And here we also define the query engine. So this is our mechanics, how we're going to search through the database. So retriever query engine needs a retriever, which is our index retriever. And it also requires some node post-processing where we requested the similarity to be computed, and we can measure some threshold for the similarity. So we need another object, similarity post-process, provided by LlamaIndex, to provide the similarity threshold. So as we did in our previous case with sentence transformers, then we provided explicit threshold 0.25. Here we provide similar threshold of 0.3 using this index and the properties of the LlamaIndex objects. So now let's go ahead and ask a little bit different questions. So the first question is, what is BERT? And now we will run the query engine with the query, and we will get a response. Now, Llama Vector Database contains all 31 chunks collected from both papers. So we do not distinguish originally where these chunks are coming from, but for us, it's just an index or the entry in the database. And let's see how this response object is organized. So let's use our favorite __dict__ property and run the keys for this. So we can see that we have 4 keys: response, source node, and metadata. So as I mentioned, once we create the database, the entries or the documents are converted into the nodes. So this source node is exactly the reference to the node inside the LlamaIndex. So let's have a look what we can get out of the node. If we call __dict with the key source node and we will get 0, we will get actually our first node from the response. And then we will recall the node itself. And then again, we will have to apply this __dict__. Then we can actually check the metadata for the node, and that's where we will get the file name. So this is how complex organized this hierarchy of the objects. So within the search node, we will have a list of nodes, and once we pick up the node, we can get the properties of that node. So let's go ahead and perform a similar operation of getting our answers, questions, the paper, and the text and the score. Let's create a data frame using these columns and loop through our response. In our case, we are going through top 7 responses, and we will pick up the score. We will take the file name, which is actually our paper name, and we'll actually get the actual text chunk, which fits the best to answer the question. And this is our output data frame. So here we can see the question. So question is everywhere is the same. Remember, these are top 7 chunks we have selected. Here you can see the similarity score. Here it's sorted from highest to lowest within like a range of 7 top responses. And here you can also see the paper where the particular text is originated from. And for this answer, to answer the question, what is BERT? The 5th and 7th answers are coming from the BERT paper itself, and the rest is actually answered by attention is all you need. Now let's do the same exercise for what is multi-head attention. And we apply the same technique. We build the same data frame. The only thing different is our query, but the approach is absolutely the same. We run the query engine against the query and get a response. Let's get the data frame for our second question. So here you can see what is multi-head attention, and here is the answer. Again, here you can see similarity scores, their paper. In this case, no answer is coming from the BERT paper. All the answers are coming from the multi-head attention, which is reasonable because the multi-head attention is described in depth in their attention is all you need paper, rather than BERT paper is specialized in more narrow application of transformer models rather than the basic theory of transformers. And finally, let us ask one more question. What is transformer? So let me correct this. So here now we have a correct answer. And now let's ask the question, what is a transformer? So here we have the same similarity score, the paper. Again, it's a mixture of the answer is coming from both papers, from BERT and from attention is all you need. And we can also see their text chunk from the corresponding paper. So in order to finalize this exercise, let's do the same merging of the data frames. Let's create a new variable, not to overlap with the previously defined variable in their semantic search. And now we see that we have basically 21 entry. So there are like 3 times by 7 top answers. And again, we have the question, score, paper, and the text. Now it's done for all the questions and contains all the information collected from our previous steps. And now let's do the same operation as we did in the semantic search. Let's group and make this merge data frame look better. And here we go. So we have the question, what is BERT? And we have the paper. And every question coming from that paper. We have the question, what is transformer? Then we have a BERT paper. And the answers coming from that paper. And we have attention paper and the answers coming from the attention paper. And then we have a question, what is multi-head attention? And we can see, again, there is only one paper, which is attention, and we see all their responses coming from this particular paper. So this is our complete merge data frame. So before I conclude, let me summarize. Here we learned a lot of things. So first of all, we come to know about LlamaIndex, and we use LlamaIndex data loader to parse our PDF files, which contain our research papers. That's where we get the document produced by LlamaIndex, and that's how we collected their chunks of text distributed across the papers. Then we did some preprocessing of those text chunks, and we collected the text chunks corresponding to a single paper to be in one place, so we can run a question answering using the large language model QA mode. So to do this, we used a Roberto-based Squid 2 distilled model, and we used Transformers library by HuggingFace. And for our pipeline, we used question answering mode. So that's how we operated. And the answers in this case, they were very short and not often to the point. Next, we have changed our approach and we did a semantic vector search. In this case, we were scrutiniously analyzing each text chunk and we converted each text chunk into embedding vector, and then we computed the similarity between embedding vectors for the text chunks and the questions. And that allowed us to be more accurate and more precise in selecting their text chunks which better answer the questions. And then we went even further and we computed similarity within a single chunk. For this purpose, we split our text chunk into sentences, and we compute a similarity between embedding for each sentence in the given chunk and the corresponding embedding of the question we are asking. This allowed us to visualize the whole text chunk by highlighting most relevant pieces in lighter color and highlighting less relevant pieces in deeper color, so we can immediately read the pieces of text which are more relevant to the question we ask. So that was a deep dive hands-on with Semantic Vector Search, and then we used LlamaIndex functionality to do the same operations which we have done by hands using similarity metrics explicitly. And finally, we got our answers in the form of unified data frames. So this concludes this video. I hope you like it. Please like and subscribe if you do, and I see you in the next videos. Thank you.